Dear students, welcome to My Dream Academy, Dilshanagar branch. Okay, so today we will discuss the applications of Biot Savart Law. Already we have derived what is the equation, what is the magnetic field due to the current carrying conductor at a distance or from the current carrying conductor. Okay, so in the last class we have derived what is the magnetic field due to the current carrying conductor at a distance or, that is B equals to mu naught I by 4 pi into ideal sin theta by r square. That is a magnetic field due to the current carrying conductor at a distance r. So now, in this case we have to discuss what are the applications of this Biot Savart Law. Now, so first case for linear currents, if currents are, okay, current carrying conductor or wire is along the straight line, okay, what are the magnetic fields at different points? Okay, so if the conductor may be finite length or infinite length or semi-infinite length or in circular shape, okay, so what are the magnetic fields? What are the magnetic fields due to the current carrying conductors? Okay, so now we will discuss. Now consider first case for linear currents. In this one, first one, a current carrying conductor. Consider one current carrying conductor carrying a current I. So what is the current passing through the conductor? That is I. Now this is a current carrying conductor. So we have to measure the magnetic field at a distance or from the current carrying conductor. What is the magnetic field at a distance or from the current carrying conductor? Now, so one end of the wire, this is one end of the wire, this is another end of the wire. One end of the wire makes an angle alpha at measuring point. Okay, this end of the wire here makes an angle alpha. Other end of the wire or conductor makes an angle beta at measuring point. So this is a measuring point. We are measuring magnetic field at this point. Now, so by modifying this equation, we will get the magnetic field at this point in terms of alpha and beta. Magnetic field at a distance or from the current carrying conductor, magnetic field, induced magnetic field induction, magnetic field at a distance or from the current carrying conductor, from the current carrying conductor is current carrying conductor, carrying wire or conductor is, okay, that value B equals to, in terms of alpha and beta, mu naught I by 4 pi r into sin alpha plus sin beta. Okay, we need not derive this formula for entrance point of view. Remember this formula. What is the magnetic field at a, now magnetic field at a distance r, by modifying this equation we will get the magnetic field at this point, okay, in terms of alpha and beta. B is equals to mu naught I by 4 pi r sin alpha plus sin beta. Remember this formula. Okay, sin alpha plus sin beta we need not derive, and by modifying this equation we will get this formula. Okay, so it is magnetic field B at a distance r from the current carrying conductor. The ends of the conductor makes an angle alpha and beta at the measuring point. Okay, so the same equation we can write in terms of theta 1 and theta 2. Now at the end of wire, this end of wire, at the end of wire angle is theta 1. Another end of the wire angle is considered theta 2. Okay, what is the equation? Magnetic field at a distance r. So what is the magnetic field at a distance r in terms of theta 1 and theta 2? Okay, so now this is, we can consider one right angle triangle. Now sum of angles in a right angle triangle is 90 degrees. Sum of angles in a triangle is 90 degrees. Okay, this value is already 90 degrees, means the sum of remaining two angles should be 90 degrees. Now from this equation we can write, from this diagram we can write angles theta 1 plus alpha should be equals to 90 degree, because sum of angles in a triangle, that should be 180 degrees. Already it is 90 degrees, right angle triangle. So the remaining angles, sum of the remaining angles should be equals to 90 degrees. Okay, so from this equation what is the value? Alpha. So alpha we can write 90 minus theta, 90 degree minus theta. Similarly, consider other right angle triangle, another right angle triangle. Now this is another right angle triangle. This is 90 degrees, means sum of angles in a triangle, that should be equals to 180 degree. Already this is a 90 degree because it is a right angle triangle. Now the sum of remaining two angles, that should be equals to 90 degrees. So from this right angle triangle diagram, we can write sum of remaining two angles means theta 2 plus beta, that should be equals to 90 degrees. Theta 2 plus beta, that is equals to 90 degrees. From this equation we can write beta equals to 90 minus theta 2, 90 degree minus theta 2. Now substitute alpha and beta values. So in this equation we will get the magnetic field in terms of theta 1 and theta 2. So what is the magnetic field at a distance r? B equals to mu naught I by 4 pi r, mu naught I by 4 pi r into sin alpha plus sin beta. So what are the angles alpha and beta in terms of theta 1 and theta 2? 90 minus theta 1, this value. Now this is the 90 minus theta 2, values is alpha beta, substitute in this equation. We will get the magnetic field in terms of theta 1 and theta 2. So magnetic field B is equals to mu naught I by 4 pi r, sin alpha means sin 90 minus theta 1 plus sin 90 minus theta 2. Okay, that value will become, so B is equals to mu naught I by 4 pi r. Okay, sin 90 minus theta, that value will become, so cos theta. Okay, cos theta 1 plus cos theta 2. So remember this formula. These all formulas are used, okay, to measure the magnetic field at different points. Okay, so remember these formulas. Now what is the magnetic field at a distance r from the current carrying conductor? So here alpha and beta are angles at the measuring point. Okay, theta 1 and theta 2 are the angles at end of the wire, at end of the wire. Remember these two formulas to find the magnetic field. Okay, let us see another formula. If the conductor is infinite length, okay, both ends are infinite, carrying a current I, so infinite conductor, this end is very long and this is end is also very long. So infinite means it is not infinite length. If it is very long, we can consider as a infinite. Okay, so now consider one conductor, the length of conductor is very long, or we can consider infinite like this. Now both ends are very long, that is indicate with the dotted lines like this. Now carrying a current I, what is the current passing through the conductor? I. So now due to this current carrying conductor, what is the magnetic field at a distance r? We have to measure the magnetic field at a distance r from the current carrying conductor. Conductor is very long, infinite length. Now in this case, what are the values of alpha and beta? Okay, alpha means one end of the conductor makes at this point, angle makes at the measuring point. If it is infinite length, alpha values increases like this. Now this is alpha. If alpha length is increases, alpha angle is increases, and at infinite length means it will become exactly 90 degrees. Okay, so this is alpha, angle between these two. Actually if it is finite length, now this is alpha. If length of the conductor is increases, length is increases, this alpha angle is also increases. At infinite length means it will become vertical. Okay, the angle between these two is 90 degrees. In case of infinite length, alpha will become 90 degree. Alpha value is 90 degree because it is extended to the infinite length. Similarly, what is the beta value? Okay, now this is angle beta. Okay, this is the angle beta. If length increases, this beta value is also increases. Finally it will become 90 degrees. Okay, so it is increases and 90 degrees. Now in case of infinite length, alpha and beta both are 90 degrees. Now the magnetic field at this point at a distance r from the current carrying conductor is, so what is the magnetic field? Already we have derived a formula in terms of alpha and beta, that value is mu naught I by 4 pi r into sin alpha plus sin beta. So what are the values of alpha and beta? 90 degrees. Substitute the alpha and beta values in this equation. We will get the magnetic field at a distance r, that is mu naught I by 4 pi r into sin alpha means sin 90 degrees, sin beta sin 90 degrees. How much we will get? Sin 90 value is 1, mu naught I by 4 pi r into 1 plus 1. Okay, 2 to 1 times, 2 times, 2 1 times. Now finally we will get the value magnetic field at a distance r due to the infinite wire or very long wire, that is mu naught I by 4 2 pi r. Remember this formula. Okay, so for solving the problems it is very useful. Okay, they will mention the infinite wire, so in that case directly substitute this value. Okay, right. Second one is another application. Fourth one is this: if the conductor is semi-infinite, semi-infinite, or this is also called as, okay, infinite at one end, one end. Okay, magnetic field due to the semi-infinite wire or infinite at one end. Now consider this is a current carrying wire or conductor carrying a current I. One end is fixed, another end is extended to infinite, means very long. Okay, so conductor other end is very long, one end is fixed. Okay, so now, so conductor this side is started here, so at this point is fixed, and this side is infinite length, it is extended to the other side is infinite. One end is start from here, so why conductor is start from here means it is fixed point. Okay, this is a fixed point, this end is extended to infinite. So like this, it is a fixed point, this end is extended to infinite. Now what is the magnetic field due to the infinite, semi-infinite wire at a distance r from the end? Okay, so at a distance r from the end, one end, fixed end. Now what is the magnetic field? In this case, if it is extended to infinite length means alpha will become 90 degree. Okay, so there is no length this side. What is the value of beta? Beta will become 0. Now alpha and beta values substitute in this equation, we will get the magnetic field at a distance r from the current carrying conductor. So it is a semi-infinite. Now substitute these values. Mu naught I by 4 pi r sin alpha plus sin beta. So what is alpha value? Okay, mu naught I by 4 pi r, alpha is 90 degree, and beta value, what is the beta? 0. So this will become mu naught I by 4 pi r, this value is 1. Remember this formula. Okay, what is the magnetic field, induced magnetic field at a distance r from the semi-infinite wire? Okay, one end is fixed, another end is extended to infinite. Remember this formula. For infinite wire or very long wire, what is the magnetic field at a distance r? Mu naught I by 2 pi r. So for semi-infinite wire, mu naught I by 4 pi r. So these are the magnetic fields due to the semi-infinite and infinite. Okay, remember these two formulas. Finite length, conductor having some finite length. Okay, now consider one conductor carrying a current I. What is the current passing through the conductor? I. Right. Now what is the length of this conductor? L. The total length is considered as L length. Now what is the induced magnetic field at a distance r from the conductor? That is, we have to measure. So what is the magnetic field at a distance r? Okay, this is one finite length. So we have considered this point from the midpoint. So this length is considered L by 2. It will become L by 2, and this is also L by 2 length. Okay, so now one end of the wire makes an angle. Okay, this length is L by 2 length. Now this is also L by 2. Now one end of the wire, this is one end of the wire, another end of the wire. One end of the wire makes an angle alpha at the measuring point, another end of the wire makes an angle beta at the measuring point. Now, so this is one right angle triangle, this is r, this is L by 2 side, this is another side, so this will become hypotenuse. What is the value of hypotenuse? That is under root of side square plus side square, r square plus L square by 4. Okay, now similarly this is one right angle triangle. Now these two are sides adjacent, okay, opposite adjacent. Now this will become hypotenuse. Now what is the value of this value? That is under root of r square plus L square by 4. Now what are the values of sin alpha, sin beta? Okay, we will get the same values, both are same. Sin alpha, sin beta, we will get same values. Sin alpha equals to sin beta equals to, so what is the sin angle? For a triangle, okay, sin angle means opposite by hypotenuse. For alpha, opposite is L by 2. Okay, opposite by hypotenuse means under root of, so what is the value? R square plus L square by 4. Sin beta value is also, okay, opposite means L by 2 by hypotenuse. What is the hypotenuse value? R square, under root of R square plus L square by 4. Now substitute sin alpha and sin beta values, okay, in equation mu naught I by 4 pi r sin alpha plus sin beta. Substitute in this equation, then we will get magnetic field due to the finite wire mu naught I by 4 pi r into sin alpha sin beta, both are equal. We can write 2 times of, okay, what is the value? 2 times of this value, sin alpha sin beta, both are equal means 2 times of this value. L by 2 by under root of r square plus L square by 4. 2 gets cancelled here. Magnetic field is mu naught I by 4 pi r into L by under root of r square plus L square by 4. That is the magnetic field due to the finite wire. Okay, so we are consider the point from the midpoint at a distance r from the midpoint. Suppose the same finite wire, okay, so what is the magnetic field at one end of the wire? So finite one. Now consider one conductor, length of this conductor is L. Now this is one end, this is another end. Now what is carrying a current I? Magnetic field at a distance r from the one end. So at this point, magnetic field at a distance r from the midpoint. Now in this case, if you want to measure the magnetic field at a distance r from the one end of the wire. So anyway, in both cases, the length of wire is L. So one time here we are measuring the magnetic field at a distance r from the midpoint. So in this case, we are measuring the magnetic field at a distance r from the one end. Now in this case, what are the beta value? What is the beta value? Beta will become 0. There is no length, okay, in downward direction. What is the alpha value? Alpha value means this is the end of the wire, this is the measuring point, the angle between these two is called, okay, so this end of the wire makes an angle, some angle at measuring point, that is the alpha. So now this is side, this will become hypotenuse, this is one right angle, triangle. What is the hypotenuse value? R L square plus, or we can write R square plus L square. Now in this case, sin alpha value will become sin alpha opposite by hypotenuse. What is opposite? Opposite is L. What is the hypotenuse? Under root of r square plus L square. Okay, hypotenuse value. Now substitute this sin alpha value in this equation and beta value will become 0 here. Anyway, finally we will get the magnetic field at this point, that is mu naught I by 4 pi r into sin alpha plus sin beta. Beta value, what is the beta value? Beta is 0. Okay, so this is a 0. The remaining sin alpha value is here. Now magnetic field B equals to mu naught I by 4 pi r into sin alpha values L by under root of r square plus L square. That is the magnetic field. Okay, remember these formulas in case of linear currents. First one is, okay, finite length, infinite length, semi-infinite length. Okay, next application is circular currents. Okay, current wire may be straight or circular. Already we have discussed if the current wire is along the straight line, what are the applications, what is the magnetic field due to the infinite wire and semi-infinite wire, if it is finite length. Okay, so in the next case we have to discuss what is the magnetic field due to the magnetic field induction due to the circular currents. Now here, first consider arc. What is the magnetic field? Magnetic field induction at the center of current carrying arc. Okay, now consider arc means a part of circle. Now this is a arc, now carrying a current I. Now the radius of this arc, that is considered small r, this is the radius. This angle made by the arc at the center is considered theta. Okay, now if it is carrying a current means every current element induces a magnetic field. Now this is also carrying a current. Due to this one, some magnetic field is induced at the center. We have to measure what is the magnetic field induced by this arc. Okay, current carrying arc. What is the magnetic field? Okay, so now we have a one formula. We need not derive. Okay, directly we can write formula. What is the magnetic field at the center of arc? That value is B equals to mu naught I by 4 pi r into theta. 4 pi r into theta. Where theta we have to consider in terms of radians. Where theta is in radians. In radians means suppose it has given the angle made by the arc, that is 60 degree. We need not consider 60 here. Okay. So convert into the radians. What is the radians? Radians means pi by 3. Substitute pi by 3 here. Okay. Angle always here consider in terms of radians, not degrees. Okay. That is considered in radians. Okay. Now due to the arc, what is the magnetic field at the center? That is mu naught I by 4 pi r into theta. Okay. Now if we consider complete coil, current coil, second one is current carrying coil, current coil. Coil means complete circle. Now what is the angle value? Angle theta for complete circle 2 pi or 360 degrees. Now consider current carrying coil. Now this is one coil or circle, complete circle. Now carrying a current I through it. Now what is the magnetic field induced at the center? Magnetic field induced at the center of this coil. So what is the formula? Now if we consider a arc, what is the magnetic field at the center? This is the formula. If it is a complete circle, what is the theta value? Theta value is 2 pi. Okay. Now consider here for formula, substitute theta value mu naught I by 4 pi r into theta for arc, magnetic field induced at the center of arc. But here instead of arc we are consider complete circle. Now what is the angle made by this circle? That is theta equals to 2 pi. Magnetic field at the center mu naught I by 4 pi r into theta value is 2 pi radians. Now pi cancel here, 2 1 times, 2 2 times. The magnetic field at the center of the coil mu naught I by 2 r. Remember this formula directly. Now in case of current coil, what is the magnetic field induced at the center? Remember this formula mu naught I by 2 r. Okay, mu naught I by 2 r. Directly remember this formula. If it has n number of turns, okay, only one turn, this is the magnetic field. If it is wind on the number of turns, okay, n number of turns, what is the magnetic field? So due to the only one turn, this is the magnetic field. Now for n turns, what is the magnetic field? We can write like this: for n turns, n number of turns. Okay, now n number of turns means like this. Okay, first turn, second turn, third turn, it is wind like this. Okay, what is the induced magnetic field at the center? Same current is passing through all turns. Magnetic field at the center B equals to, due to the one turn, this value n turns means n into mu naught I by 2r. This is the magnetic field at the center of the coil. Okay, so next consider semicircular coil. This is the one complete coil. Now if it is a semicircular coil, semicircular coil. Now semicircular coil means angle is pi radians like this. Consider now this is one semicircular current coil carrying a current I. Now the radius of this semicircular coil is considered r. What is the magnetic field induced at the center? We have to measure this value. Okay, this is one current carrying conductor. Every current element induces a magnetic field. What is the magnetic field induced at the center of this semicircular coil? So now substitute theta value in this equation. What is the for arc? Due to the arc, what is the formula? B equals to mu naught I by 4 pi r into theta. What is the theta value in this case? Theta is pi radians. B equals to mu naught I by 4 pi r. 4 pi r into theta value is pi cancel here. B equals to mu naught I by 4 r, mu naught I by 4 r. This is a magnetic field induced at the center of semicircular coil. For complete coil, what is the magnetic field? Mu naught I by 2 r. For semicircular coil, what is the magnetic field? Mu naught I by 4 r. For arc, due to the arc, what is the magnetic field at the center? That is mu naught I by 4 pi r into theta. So remember these formulas. These are used, okay, most important formulas. Okay, these are useful while solving the problems. Next one is 1/4 circle. This is also called quarter circle. Now for 1/4 circle, what is the angle theta value? Pi by 2 90 degrees, pi by 2 radians or 90 degrees. 1/4 circle. Now it is lies between x and y axis like this. Now what is the angle between x and y axis? 90 degrees. Arc, okay, part of circle is lies between these two axes. carrying a current I. Now what is the angle here? That is a 90 degrees. Now what is the radius of this 1/4 circle? R. Okay, so a complete circle is divided into 4 equal parts. One of the part is 1/4 circle or quarter circle. Now what is the angle made by this quarter circle? That is pi/2 radians. What is the magnetic field induced at the center of this 1/4 circle? Now we have a formula for arc magnetic field at the center, that is mu naught I by 4 pi r into theta. Okay, in case of 1/4 circle or quarter circle, the theta value is pi/2 radians. Now substitute pi/2 radians. In this case we will get the magnetic field due to the 1/4 circle, pi/2. Okay, so here pi cancel. How much we will get magnetic field? B is equals to mu naught I by, so 4 into 2 8 r. That is the magnetic field at due to the 1/4 circle. Next one is 3/4 circle. Now next one 3/4 circle. So what is the angle due to the 3/4 circle? So 3/4 circle means one quarter circle, one semicircle. Now this is one semicircle. Okay, semicircle, and another one is 1/4 circle. The total will become 3/4 circle carrying a current I. The radius of this one is r. Okay, 1/4, 1/2 circle means pi/2 values, theta value pi/2 or pi radians, sorry. Okay, pi radians for semicircle. For quarter circle, this is a pi value, this is a pi/2. The total value will become 3 pi/2. Due to the 3/4 circle, theta value is 3/2. Okay, so 3/4 circle means one semicircle, one quarter circle. Okay, that is the 3/4 circle. Now due to the semicircle, angle is pi radians. Due to the 1/4 circle, angle is pi/2. Okay, the total angle in this case is 3 pi/2. Now what is the magnetic field at the center of this 3/4 circle due to the current carrying? Now magnetic field at the center formula mu naught I by 4 pi r into theta. What is the theta value in case of 3/4 circle? In case of 3/4 circle, theta value is 3 pi/2, and substitute in this equation we will get the magnetic field at the center due to the 3/4 circle. Now that value will become mu naught I by 4 pi r. Theta value, what is the theta value? Theta is 3 pi/2 radians. Now pi gets cancelled here. 2 into 4, that is 8. 3 mu naught I by 8 r. Remember this formula. Okay, for 3/4 circle, what is the magnetic field at the center? 3 mu naught I by 8 r, where r is the radius of 3/4 circle. Radius of the circle, I is the current passing through the circle. Mu naught means, what is the mu naught? Permeability, magnetic permeability of air or free space. Now in case of 1/4 circle, what is the magnetic field at the center? That is mu naught I by 8 r. Again, r is the radius of the circle. Remember these formulas. Due to the arc, what is the magnetic field due to the arc? Mu naught I by 4 pi r into theta. If you remember the magnetic field due to the arc, we can derive any part. For complete cycle, okay, theta value will become 2 pi. For semicircle, theta equals to pi. For 1/4 circle, theta equals to pi/2. For 3/4 circle, theta equals to 3 pi/2. By substituting those values in that arc formula, what is arc formula? B equals to mu naught I by 4 pi r into theta. Then we will get remaining all formulas.